Good morning, class. So today we'll continue further with the 15th and almost we'll be able to complete this. So next is the critical parameter management. So basically once the product moves into manufacturing, any deviation that is seen in the system performance, that is during assembly or at end of the production line, can be rechecked by critical parameters. So basically whenever you would have seen the 2D drawings or 2D detailed drawings, always there will be some critical dimensions. So after manufacturing only or after getting assembled of that part into subsystems, then only you will be able to check that manufacturability of that critical assembly. So those things becomes the critical parameters. Those critical parameters represent enabler to function or to test true to any malfunction that occurs and can be used throughout the life cycle of the product. So that can be avoided. Hence, once you eliminate, if the critical dimensions are produced well within the tolerance zone or well within the specifications, then that will improve the product life cycle. The process of management of critical parameters is divided into three parts for design activity. The first one is the development. Once a concept is conceived, many of the critical parameters are not known. That is true. Some of the critical parameters are known either from previously similar design or analysis of functional system. Finally, critical parameters are developed whose general sensitivities to the response of functions are known. During this process, optimization of assumed critical parameters will take place and also indicate additional possible parameters which are critical and also be considered. This part of critical parameter management is called as critical parameter development. So what you mean by critical parameter development is that once you design, you can say that while designing a part, will not be able to know what are the critical parameters. So only when after the part being manufactured or one or two parts have been manufactured, then only you will come to know what are the critical parameters in manufacturing the particular component with respect to design. So at that time you also may come across with new critical parameters. So these all things are analyzed and this is called as the critical parameter development, and also we need to optimize those critical parameters. Implementation. Once critical parameters are used to define design intent, they can be used to prepare drawings or design files which is vehicle for manufacturing of parts. So once critical parameters are defined, then they can go for finalizing of the design, and then which will become a basic for manufacturing of the parts. So this is also called as parameter implementation process. It means that drawings meet the design intent by monitoring critical parameters. Then drawings are released for building. So whenever you implement a critical parameter, what happens is that then it means that the design is already finalized, and then the final 2D drawings can be reduced to the manufacturing department. So hence there will be no much revision of the drawings that is going to take place. So critical parameter review takes place. Whenever critical parameter review takes place, then there is a revision of the drawing takes place. So whenever all the critical parameters are studied, then no further revision of the drawings is going to take place. That will be the final design for a particular part. So then the audit. Here the parts are manufactured following release of the drawings. This process checks whether parts according to the drawings or whether drawing is wrong. Here in audit what happens is that the parts are manufactured with respect to the drawings or the dimensions or the tolerances or GD&T symbols that are presented in the drawing. According to that, the part is manufactured by using the suitable available machines and tools. And after manufacturing the parts, the dimensions or the critical parameters are checked with respect to the dimensions. Then we are going to see whether the manufacturing process has to be changed to meet the requirements of the drawings, or whether the drawing has to be changed to meet the requirements of the manufacturing process. So this is how it looks like: the development phase, the implementation phase, and the audit phase. So in development phase, we told that CP identification, design of experimental hardware is going to take place. You are going to assess manufacturability, optimize CP, test performance, redefine CP, establish design intent. So these all things what we have discussed will come under the development. If you want to represent in the diagrammatic format, this is how you are going to represent. Then the implementation phase, in again implementation phase, you are going to implement CP on drawings, compare drawings with design intent, identify shortfalls and risks, modify design intent to meet the latitude requirements. Then audit, measure CPs on hardware, identify shortfalls and risks, modify hardware or design intent. So then critical parameters development process, how it is going to take place. First, identify by observation, analyze or test all control factors or critical parameters. First you need to identify or observe the process, and then you need to identify the critical parameters that are associated with it. So basically in the first you are identifying the critical parameters, then list all critical parameters based on current knowledge. So you need to list all the critical parameters whatever you identified based on your current knowledge. Then assign nominal values and tolerance based on current knowledge. So you need to assign the nominal values for those critical parameters, and also importantly you need to assign the tolerance based on your knowledge. And then design hardware for optimization experiments, and you need to design the hardware for optimizing these critical parameters. And then the audit. Then the audit design comes into picture, where does design meet CP intent or no. We need to check whether the design what you have done is going to meet the critical parameters or no. If yes, then is design good for manufacturing, you need to check. If yes, then you need to build the hardware and then you need to go for the manufacturing. Now, if the design is not meeting the critical parameters, no, then you need to modify the design. Again you need to go for the audit. Further, if design is not manufacturing, again you need to go for the modification of the design, and then again you need to go for the audit program. Again you need to recarry the process of whether the design is meeting the critical parameters or whether the design is easy to manufacture or it is manufacturable. So next, after audit hardware, we need to check whether the hardware meet CP or design intent, whether the hardware is going to meet critical parameter or design intent. If yes, then design experiments to optimize control factors you need to look for, and then you need to define measured output or response with respect to the performance test, and then you need to go for optimum control factors. What are the factors you are going to control optimally, and then set to optimum control factors and normal set points and test for the performance. You need to set, or that means what you are doing over here, we are basically optimizing the critical parameters, and then after optimizing we need to check whether the measure output meet the performance. If yes, then freeze critical parameters design. If no, then recheck the hardware review designs, and then again if it is if you check that, then we need to go for modify hardware, and then again the process begins with the audit hardware. If the rechecking of hardware is not suitable, then you need to redefine the critical parameters, and then again you need to, after redefining the critical parameters, you need to assign nominal values and tolerance based on your current knowledge, and then you need to proceed the further steps. This is how the critical parameter development process works. So basically it starts from identifying certain critical parameters and listing those critical parameters and then building the design and making the audit and then optimizing those critical parameters, and then you need to check the optimization by the test. If the processor is meeting the requirements, then you need to freeze the critical parameters. If you feel that the process is the test output or the test results are not meeting the specific requirements, then you need to change the critical parameters. Then again you need to do the process starting from the first point, that means assigning the nominal values, and then again audit, design, etc. So After that, then critical parameter implementation process. First it was a critical parameter development process, now critical parameter implementation process. In this, enter design nominal value and tolerance range. So you need to enter the nominal tolerance zone for each of the critical parameters over here. Then compare design with design intent. This is important. You need to compare the design with the design intent, and then whether the design range within design intent tolerance. If yes, then approve design for building. If no, then can design range be brought within the design intent tolerance? We need to check. If yes, modify design and then again enter design nominal and tolerance range. If no, we need to go for identify expected failure mode. We need to identify the expected mode of failure, and then can failure mode be accepted, whether the whatever you are identified the mode of failure, whether that mode of failure is expected in the current scenario for that particular part. If yes, then approve design for building. If no, then can parameters be changed to broaden latitude? We need to change the whether we need to check for to change the critical parameters. If no, new technology selection. If yes, then modify critical parameter design and then modify design and then enter nominal design. This is how the critical parameter implementation process works. Next, critical parameter audit process. Critical parameter audit process. So in that, first you need to measure the critical parameters on the hardware and then to check whether the measurement is within the design intent or within the design range or no. If yes, record measurement in the table and then approve for test. If no, then check parts against the drawings that are not within the design range, and then are parts to drawing, whether the parts have been transferred to drawing. If yes, does design meet design intent? You need to check. If yes, can failure mode be acceptable? If yes, then update CP chart. If no, review technology selection. And again, if design is not meeting the design intent, then rework drawings. You need to again rework drawings. That is active work. If you are reworking the drawings, what will it happen to? It will be result in reworking of the parts, which incurs cost. So basically it is voided, and then it is again measured back to the critical parameter. So this is how the critical parameter audit process works. Next, critical parameter status or assessment of critical parameters to its stability. The list of critical parameters, their nominals and tolerance serves to represent the design intent. This set of data for any functional area is continually being updated as optimization occurs and further refinements are made due to data generated. If the design process were to wait until we get all data and stable before design was allowed to start, the duration is too long, which becomes unacceptable and uncompetitive. Next, the design process can be started without full information available. The design process can be started without any full information that is available, but not finalized. This is important. We can start the design process, but we can't finalize without full information until complete set of data is known. That is true. In order to define clear confidence levels in data, each of the critical parameters is assessed to its level of stability. If the critical parameters are stable, then only the confidence in building up of the data increases. Hence, we start to believing the data or the design. The stability is defined by three categories. The first one is the defined. This means critical parameters is stable and has been optimized either during current program experimentation or by mature knowledge pending. The next point, critical parameters is the midst of being optimized. So it means first step is already defined. That means critical parameters, they are stable and has been optimized. Then there is no fear in changing the design. We have the confidence in our design. So the status again is that second one is the pending. That means it is not yet processed. That means critical parameters is in the transition period of being optimized. So here nominal and tolerance values are defined, but they may change as subjected to optimization process. So in pending, the optimization process is still going on. So whatever the tolerance zones we have specified for that particular critical parameter, they are not finalized. So they may change depending upon the change in the design, and also it may require the change in the design means it may require rework also. Hence the status is pending over here. And the third status is undefined. Here the critical parameters are evaluated only at the minimal level and likely going to change and not based on engineering valuation. Here only critical parameters are identified and they are not being optimized or not being taken into optimization. But once you go on further studies, these critical parameters may also change. Hence, the status of these critical parameters are undefined. So there is an example, you just can have a look at this example. So for particular component, what are the critical parameter status like undefined, pending and defined. So all the list have been given for the subsystem number and the number of critical parameters with respect to undefined, pending and defined are represented on the y-axis. Just you can have a look. This is how a number of parts in a subsystem with respect to the critical parameters with respect to the status such as undefined, pending and defined can be done by doing different shades with respect to different status of the parameters. See again you can assess the critical parameters with respect to low risk, moderate risk as well as high risk. This can also be done. FMEA. So this thing we have left in the, I think in third or fourth unit because we need to consider it in this chapter also. So I have left it over here and I am covering it over here. Failure is defined as consequences of not meeting customer requirements. That is true. Failure, when you say that component is going to fail, when it is not meeting the customer requirements and when it is not doing its intended function. This method helps the engineer or team to identify areas of design or technology that require further for reliable advancement of the technology. So this method helps when the component is going to fail, and because of improving that, the reliable component can be built for the use of the customer. Consider example of a rubber coated roller. So I just considering an example of a rubber coated roller. One potential of failure may be debonding of the rubber, metal coated rubber. One potential failure may be debonding of the rubber from the metallic core, which causes malfunctioning of the machine. So the bonding between the rubber and metal is very low. That may be the reason, or the specific coating procedure, that is the coating procedure is not good to test rubber for its effectiveness. There are three factors that have been taken into account for FMEA, that is severity, occurrence and detection. Severity, occurrence and detection. In severity, failure in terms of customer dissatisfaction. So how much severe it is. Then customer reacts strongly to failure if it puts him into danger. That is very severe. So that means if he is driving a vehicle, new brought vehicle, suddenly the brake fails, then that is a severe failure, because he expects that is of a new vehicle that is not going to fail. So but suddenly within 100 kilometers or 200 kilometers if the brake fails, that is very high chance, but that kind of an example is considered as very severe. Occurrence, it depends upon type of failure and robustness of design. It also depends on product's age and reliability. Occurrence, how often the particular failure of part is occurring, or particular failure of product is occurring. Whether the occurrence is very often or whether occurrence is not very often. It again depends upon the how old the component is or how new the component is, according to which environmental condition it is put, and how the customer is using with, and whether he is following the particular guidelines given on that particular product or no. And again, basically it defines the reliability. So that is nothing but the mean time between failure. Detection. Some failures are not easily detectable by the development process. Some failures are very difficult to detect. The above three categories are rated to assess their level using judgment of the engineer. So it is again based on the judgment of the engineer. The product of these three numbers is called risk priority number. Basically the product of these three parameters what here discussed is called as the risk priority number or RPN. A low RPN is regarded as a problem for low priority, whereas those of higher RPM is regarded as a problem having major impact on customer satisfaction. This is very critical. So it has to be median. If the RPN is low, it is regarded as a problem of low priority. Okay, or if the RPN is very high, then it will have a severe impact on the customer satisfaction. So example of, we are taking a ballpoint pen. So in ballpoint pen, what we are seeing the sum of the parts that makes the ballpoint pen and their functions, then their potential failure mode, potential effects of failure, severity, potential causes of failure, occurrence. We are going to check how well the potential of failure be detected, detection and RPN when we are mentioning it, and then the actions. So this one example we will see, and then we will conclude this FMEA. So if you consider a ballpoint pen as a product, some of the parts which consist are outer tube, ink, ball and sheet, inner tube, plug, outer tube. So these are the parts which makes the ballpoint pen. So these parts are assessed with respect to function, potential failure mode, potential effects of failures, severity, potential causes of failures, occurrence, how will the potential failure be detected, detection, RPN and actions. So for the first part, that is the outer tube, what is the function? Its function is to provide grip for writer. Potential failure mode, the hole gets blocked. Potential effects of failure, vacuum on ink supply stops flow. Vacuum is created because of which the ink supply stops. And severity is 7. That means it is highly severe. Potential causes of failure are debris increase into hole. Occurrence, it is 3. How will the potential failure be detected? Chuck clearance on the hole. Detection, you can detect it very easily, it is 5. RPN number, risk priority number, what is given is 105. Actions what have been recommended are make hole and the remove cap. Similarly, you can look all the parts and their functions, potential failure mode, potential effects of failure, severity, potential causes of failure, occurrence, how will the potential failure be detected, detection, RPN and actions. Here you just have a look of all the parts that consist of ballpoint pen. Similarly, we can have a look of the last part also. It is the outer tube. The function of the outer tube is to provide grip for writer. Hole gets blocked, that is the potential failure mode. Severity, it is 7. Debris sink through hole, occurrence is 3. How will the potential failure be detected? Check clearance on the hole, detection is 5, RPN 105. Make hole and then the remove cap are the actions. Now here the outer tube is important part because that is what the writer is going to hold and supports the inner tube. So outer tube should not be totally sealed against the ink in inner tube, otherwise vacuum is created which may cause restriction of the ink flow. The designer incorporates small hole at side to minimize above condition. When considering potential failure modes, one of these may occur if hole is blocked. This may happen during manufacturing of care of the customer. The effect of failure will be on customer because that is he is the one who is using that product. Partial vacuum may degrade writing performance and failure occurs. The severity is 7. The debris increase into hole may be potential failure for blocking hole and it may not very likely to be happen, hence occurrence is 3. Shear. The debris increase into hole may be potential failure for blocking the hole, but it may not very likely to happen, hence the occurrence is given for 3. Controls are applied to test occurrence of failures. Pressure applied during assembly process ensures that debris present at the stage can be blown away or otherwise visual inspection is going to take place. The level of detection is 5. Multiply 3 ratings gives RPN of 106. Problem solving cycle. Sorry. So in this problem solving cycle, the process identifies 6 steps to the problem solving process. These are: identify the problem, analyze the problem, generate potential solution, select and plan solution, implement solution, evaluate solution. So basically the problem solving cycle consists of 6 steps, that is identify the problem, analyze the problem, generate the problem solution, select and plan solution, implement solution, evaluate solution. So first we start with the first step, that is the identification of the problem. Suppose you consider this is the back case of the particular cell phone and suddenly the cell phone design has been changed. So I need to change this design according to the cell phone design so that it can fit the back face of the cell phone. So the problem here is what I can identify is there is a change in the model or change in the shape of the cell phone, so that I need to change the design of this back case. Hence this back case can easily fit the back of the cell phone. So the identification of the problem is very important. So here in identification of the problem is I need to change the shape. But how? Which shape? Which shape I need to change? So that is next the analyzing part. Analyze the problem. So problem is there, but I need to analyze. So here the shape is changed. Yes. According to which drawings, what is the tolerance? Those all things I need to check. Whether the outer shape is there same or there is changes or modifications, that also I need to check. And this thickness, whether the thickness of the cell phone has also been changed. If it is changed, up to what thickness it has been changed, and what is the tolerance I need to provide for this, so that it can easily fit and can be easily removed from the back case. And with respect to this logo, whether the logo position has been changed or it is same, and whether the size of the logo is same or whether it has been changed, with respect to that I am going to provide a cutout over here. So this all things are the happens in analyzing the problem, and then What next is I need to generate the possible solutions. So I will generate 2 to 3 drawings with respect to the change in the modification of the cell phone, and then I will choose among 3 to 4 conceptual design, one design as the final design. That is the third and the fourth step. And the fifth is the, after choosing the final design, I am going to implement that solution. I am going to implement that solution, and then I am going to evaluate the solution. So that means first I am going to manufacture this part. After manufacturing, or I am going to check it. That is one thing that you can do, but that will result in cost incurrence if the part doesn't fit. So what I can do is that I will implement the solution, and evaluation can be done by using the software itself. Visual fitting of the case can be done on the visual part or visual cell phone. That means it can model the cell phone back cover, and it can model the back cover what we are manufacturing, and then see to it whether the proper fit is going to take place or not. And after having the proper fit, how it is looking, whether it is aesthetically pleasing to the customer or no, and then we need to go for the manufacturing. After manufacturing also, the important thing is choosing the type of material. The choosing the type of material also comes under generating potential solutions. So these all things happen for all the products. So for any product, these are the 6 steps to solve the problem, or you can say the major 6 steps to the problem solving process. Six tools for designer. So basically there are 6 tools for designers. In that, the first one is just to identify the problem. So what does the designer work is to identify the problem, to develop the conceptual designs. Among those conceptual designs, which one is the best suited design? So for all these 3 activities, the designer has 6 tools. These are the brainstorming, second one is the fishbone diagrams, third one is the Pareto charts, fourth one is the histograms, fifth one are the control charts, and sixth one are the force field diagrams. First, we are discussing out serial wise. The first one is the Pareto chart, named after Vilfredo Pareto, an Italian economist who worked with unequal distribution vertical bars. He uses bar to identify value of the things. The bar with greatest value is first, the one with the next larger value is second. This diagram helps the designer to view data and immediately get graphical feeling about the levels of importance of each item. It is useful when deciding which element to work on first and which will provide benefit relative to others. So obviously is that you can see the Pareto chart over here. Pareto chart over here. Suppose if a designer is working on certain components, if he gets through 2-3 design problems to solve. So I'm just taking an example. If I'm a designer, I am working in industry, and there is some higher authority, you can say some manager is sitting above me who is assigning some work, and suddenly he assigned me work of 3 to 4 parts to design, and he gives me a target of within a week you need to specify or give me the design of all the 4 parts. So I am in a confusion which one to start at first. So I know that whenever among these 4 designs, 1, 2, 3, 4, the which I am going to choose first will be finished first, and which I am going to choose will be second will finish second, and which I am going to choose it will finish third, and which may choose at last will finish at last, and sometimes it may not meet the deadline of 1 week. Hence what I am going to do is that I am going to analyze with respect to the customer point of view or with respect to the managerial point of view which is of much important among 1, 2, 3, 4. So if I feel the third design is very important with respect to the emergency of the part and with respect to the type of customer he is. I am going to reward this third as the largest value, and thus it will have the longest histogram. If I feel that the fourth is the next important design, then I am going to represent the fourth at the second level. Then if you look at the length of the histogram, it will be slightly smaller than the first. If you look at the third histogram, if I feel that the first is next importance compared to the third and fourth, then it will be represented after this, and last it will be represented the fourth. So what does it gives that whenever I look this histogram, so after coming each day to office or after some break, I feel that the one thing what I need to complete first is the third, and then I need to go sequentially. So that means depending upon the importance of that particular design to me, I am assigning the certain value. By seeing graphically, I can see that I can come to know which is of much importance and which is of less importance to me. Next, histograms. It helps graphically amount variability that lies in the process. A study about spread and shape tells condition of the process. Narrower the distribution, lesser variability in the process. So basically, next the histogram. So if you are studying any particular process, we always know that there are certain variation in the process, because the variation in the process is always there because of chance causes and assignable causes. Chance causes and assignable causes, the variation in the process is always there. So those variations are represented by this histogram or by using this bar graph. If the narrower the distribution, lesser variability in the process. If the distribution is more, then it is obvious that there is no more variation in the process. Control charts. It is another simple chart used to plot progress of particular factor within a process. So here what I can see is that if a control chart mainly consists of a center line, upper control limit and lower control limit. I'll better process this with a part of a shaft. Okay. So this is shaft which has to be manufactured. So these are like 1000 parts I need to manufacture of this particular dimension of a shaft. Now the basic size is how much? Basic size is 50 mm. And what is the upper limit? Upper limit is 50.02 mm. Lower limit sorry for that. Lower limit is 49.98 mm. So what happens is that my target value for this production of the shaft is always 50 mm. But I know that this 50 mm is not achievable, hence I have given the tolerance with upper limit of 50.02 and lower limit of 49.98. So control charts will be such that first I will mark a center line and the dimension of that I will write as 50, and upper limit I will mark, what is that? It is 50.02, and lower limit also I will mark, it is 49.98. So like one after the shaft, one shaft after the shaft, the part is going to be manufactured in industry, and after manufacturing, the lengths are measured. So length are measured. So we need to check whether the process what the shaft is being manufactured is true with respect to the specification or false with respect to the specification. So that can be easily done by plotting the control charts. Suppose the first part that has been manufactured lies between 50 to 5103. I'll represent it as first. So I'm just representing an example over here. 4. So I'm just not naming the parts. Then I'm going to connect these lines. So here, what I come across with respect to the control charts are some of the parts that have been manufactured are well within the limits of 50.0 to 49.98, but some parts are below 49.98 and some parts are above 50.02. That means here 1, 2, 3, here 4. 4 out of say 1000 parts are not meeting within specification. Then we can say that the process is out of control over here and over here. But if all the parts fall within this range, and if the if all the parts fall within this range and if well within these lines of upper limit and lower limit, then we can say that the process is in control, hence it is going to produce parts always true with respect to the specifications. Then the force field diagrams. It is used when change has occurred that create problems. The force field techniques tells that any change has two sets. Driving and restraining forces. Here you can see in the diagram, it is always represented by two diagrams. So here the driving forces and the restraining forces. This is how it is represented, the driving forces and restraining forces. With respect, we are taking an example of reduced expenditures and health threat. So here reduced expenditure is the driving force and restraining force is keeping weights down. Health threat is causes, and then the restraining force is steadiness nerves. Clothing smells, no health threat to me. Unsocial habit like smoking, fashionable. So this is how the force field diagrams are represented. So process capability, we know that. So I have studied in SQC that, so but as if it is not there for a syllabus. Next is the PDC, product development cycle. Product development cycle. So the first phase consists of pre-concept phase. Pre-concept phase is, we have already discussed. I'll just go through this slide very quickly. Just you can, because it is already discussed a number of times. So in pre-concept phase, it is identification of business needs to satisfy the market and customer needs. Technical teams are established to establish architecture and other technical proposals. Technology readiness is prepared, including resources, facilities, tools and training, etc. Whole strategy is communicated to sales and marketing to confirm that customer requirements are fully met. Key areas such as marketing, engineering, planning and manufacturing are important through initial phase of program. Good and comprehensive plan is essential for success of this phase. During this phase, a plan for next phase, that is a concept phase, is developed. The process of defining critical parameters should be initiated and combined with full functional diagram. Overall, the manufacturing engineers should be satisfied that design approach proposed is consistent with manufacturing strategy. Next is the concept phase. This is the second phase of PDC. Here, readiness of new technology is considered. Clear definition of how and when it will be launched, which requires dedicated management to develop strategy. The design is completed and frozen. In this phase, marketing aspects such as target markets, product position, pricing, servicing must be finalized. Here, design teams look forward and develop a plan for next phase. The plan includes objectives of a phase, phase exit criteria, etc. Competitive situation is assessed and response of situation is decided. Technology readiness is required to demonstrate during this phase. Product intent design is stated. Design analysis is completed. Manufacturing support team for strategy development. Next, the design phase. It is the third phase of PDC. Here, the production intent design is completed. A program launch strategy is developed and sales unit are prepared. Here, attention is given towards launching of the product. The decision plan implemented during concept phase is now implemented. Product appearance is finalized. First iteration of hardware and for testing is built. You can easily compare with the mortality cycle what we have discussed. Demonstration phase. It is the fourth phase of PDC. Objectives of this phase is to demonstrate stability and production intent design. So here, plan for all necessary hardware, spares, accessories and support launch. Minimization of variability in the parts is a key enabler for success of this phase. So the next phase is the production phase. It is the fifth phase of PDC. Full scale of production process and testing to gain management for approval for the program to go for production to launch phase. Review process takes place such as the latest business case, engineering reliability, design stability and performance, manufacturing quality, marketing, customer support, customer acceptance feedback. All preparation for launch is done and confirmed. The sixth phase, it is the sixth phase of PDC, that is the launch phase. Product is introduced to the end user in the launch phase. This phase confirms performance of the product. Problem arising in early stages of launch are identified and must be dealt quickly. Customer satisfaction monitoring is maintained throughout the phase. Senior management approval is required to transfer the product into maintenance phase. Next, the last is the maintenance phase. Here, it is the final phase of the PDC. Production of parts continue to meet the requirements of the customer. The peak of revenue and profits for product is taken in this phase. Here, the end of life strategy for product is established. So this is how the different phases with respect to the objectives in each phase are shown in this particular drawing. So root cause analysis. So here you can see in pre-concept what we are doing is that business needs identified. So that means what is the needs from the customer is identified in this pre-concept phase, and the alternate concepts are defined also in this pre-concept phase. That is before concept. What are the inputs that we are going to take from the customers? So then what is the thing we are going to get from this pre-concept is that business needs confirmation. That means I need to go for this design, so I need confirmation that whatever the customer requirements are true or false. And then architecture and technology sets are selected, business cases scooped, it is enhanced. In the concept, technology readiness is demonstrated. Targets for cost, quality and delivery is established, because of with respect to that only we are going to develop our concept designs. And then production design intent layout is completed in the concept phase. And the next is the design. Here Production design intended demonstration is done, targets are committed, launch strategy is defined in this design phase, and then the demonstration. Design stability is confirmed, product manufacturability is verified, readiness for launch is assessed, whether we need to go for launching of the product and what are the preparation we need to go for launch before launching is done in this particular demonstration phase. The next is the production. Customer testing is completed over here. Readiness for field confirmation is done over here, and the product is officially announced after production. After launch, customer satisfaction assessed against the targets. The customer satisfaction is evaluated through feedbacks of various types, and then the field audit is also completed by the field auditors, and the product improvements are planned. If there are any shortcomings we are going to get, which we are getting from the feedback, then the shortcomings are addressed by planning the improvements. Then the maintenance. Product discontinuations plans in phase need to be analyzed after a certain period of time. Product disposal is completed if we are going to withdraw the product. So this concludes the unit.